combinator is a non-deterministic choice between this and this. So one thing it can do is it can accept a new connection, which it does using this obs connect combinator. This says we can, the way to think about it is, we're specifying a reference implementation in the sense of something that's observing a trace of interactions and saying, is it good or not? So we can observe a connection happening, call it C, and then loop back adding C to the list of open connections. Or we can choose any of the open connections. We can observe somebody sending a message to the server on that connection, call it message. Then we can observe the server sending back a message, which must be last message. And then we loop back with the new message as the new last message. Okay? So lots of details left undefined, but at a high level, is it clear what this thing is doing? Good. Now here is the C code. Here it is, here it is, here it is, here it is. Okay, that was fun. Of course, I wasn't showing you C code, I was showing you Coq code generated from a C file by the CLite front end. So I think you're familiar with this from VST, but the file we were looking at just now is called main.v. Main.v is generated from main.c. Main.v is the abstract syntax tree for main.c, which I'm not going to show you, but you can find it in the DW directory. Okay, so I'm going to skip over all of that part and just ask you to believe that we can write a swap server in C, and that was the abstract syntax tree of it. On Friday, Leonard will show you how to prove that that abstract syntax tree refines this. Okay, this is a web server written in a low-level way on top of, directly on top of the POSIX sockets interface, using all of the kinds of data structures and control structures that you would need to interact with POSIX sockets. And you say receive, and you give it a buffer, and it gives you back maybe not all of the message that was received, but just a few bytes, and then you have to loop, and et cetera, et cetera. All of that stuff is what this code does. So we have connection data structures, and we have ways of updating the data structure after things happen, and we have something for accepting connections, and something for reading from connections. So it's all pretty complicated. There's quite a bit of it, but it's just a Galena transliteration almost of the low-level C code.
Does any of it come from Certicos, or is it somehow extra?
Okay, so the connection to Certicos is an excellent question. I'm not going to talk about it very much, but briefly, the Certicos team is working on implementing the POSIX API that we're relying on here. And there are some details to figure out about whether it's actually going to live inside of Certicos, or whether we're going to get to it by RPC to a Certicos guest process or things like that. But the expectation is that calls like accept and send and receive on sockets are going to be implemented by something that we get to by talking to Certicos. Other questions? Please.
Is that API currently being realized by linking against the libc, or
Yes. So currently we are not running on top of Certicos. We're running on top of Linux, or your favorite operating system, and using the real POSIX API. And the idea is to port it to Certicos sometime real soon now. Other questions? Okay. All right. And now we come to the top-level correctness property. So it's pretty short because, of course, all the details are buried elsewhere. But basically it says a swap server is correct if, and then there are two lines, and the first line is today's talk, and the second line is Friday's talk, and they are and they share an existentially quantified thing called tree, which is the C-like Galena specification that we were just looking at. So in the proof of this, which is elsewhere, tree will be filled in from the file that I just showed you. And then what we have to show is that the swap observer is refined modulo the network by this tree. And then on Friday we have to show a Hoare triple involving this tree holds of the C code. Okay, so that was the high-level overview, and where I would like to get to at the end of the next hour is to give you a somewhat detailed understanding, a kind of next cut at understanding of what that top-level theorem means, and how we prove it and how we test it. So I'm now going to slow down a little bit and go back to the beginning and tell you about the interaction trees, which are the kind of notational infrastructure on which all of this is built. So what is an interaction tree? It's an element of this type M applied to some set of events. You can call them events or you can call them effects. So for some particular type E of events or effects that we're talking about, ME is the type of trees over that set of effects. Why do we parameterize on effects? Because we use trees in all sorts of different ways. So we use trees to describe the low-level implementation of the server over a set of events that talks about POSIX socket operations. And we use trees to talk about the high-level reference implementation of the server over a set of events that talks about observing things on the network. So that's the reason for the parameterization here. So what are the possibilities? So an element of this type M of E for some particular E, and X for some particular result type X is one of three things. It can be a leaf node that says just return a value little x of type big X. So this kind of tree is a very small tree that represents a computation that's finished, and its result is X. This third one, called tau, represents a kind of computation that is not finished, but it isn't interacting with the outside world at the moment. Instead, it's taking an internal step. So it's taking a silent internal step, or some internal computation is happening. And it is parameterized by a continuation K, which is another tree. Okay, so trees, M's, can represent computations that are finished. They can represent computations that are doing some work internally, or they can represent computations that want to interact with the outside world, that are doing some interactive event. That event is called little e, and it comes from this parameter type event. And y is the result of that event. In other words, a tree with a node, a tree whose root node is called viz, is labeled with an event at the top, and kind of once that event happens, so if that event is, for example, a read, then the value read by that read will be the result of the event. And then the continuation is not just a subtree, it's a function from possible results to subtrees. So the continuation says, after the event has happened, tell me the result of the event, and then I'll tell you how we continue with the computation. And the whole thing is a co-inductive definition, parallel to the co-fixed point that we saw a minute ago, because we want these trees to be potentially infinite. Please.
In the co-fixed point before, you were using monadic notation, and I was wondering how can Coq determine that that definition is guarded?
Extends the function.
Sorry?
It extends the function?
So it expands the function is the technical answer. Let's postpone that question and come back to it in a little bit.
I'm not sure that's the technical answer either. Doesn't the bind notation be sugar directly to viz?
All right, let's stop and take a look. Where is it? All right, so the question is, why is this call and this call to the swap observer loop appropriately guarded?
So it depends on the definition of disk.
Yeah, exactly. So dist is putting a constructor in the tree because we'll come back in a minute to what dist does exactly, but it is representing non-determinism, and it represents it by putting a node in by putting an event in the tree that says there's a non-deterministic choice being made here. Why is that an external event? Because in some sense, the choice of which branch we follow is being made by the scheduler. And it's that constructor that guards these calls. I believe. Okay, so here we were. So this M thing is not something, well, it is something that we made up, but once we made it up, we discovered that lots of other people had made it up. It's a fairly canonical thing, in fact, and you can read a nice paper about it by Oleg Kiselyov and Hiromi Ishii, who call it the freer monad. So it's a thing that's known, for example, in the Haskell community. And it is, for example, in particular, a monad. So here is its bind, and here is its return. Let's see, is it worth going through the details? Yeah, probably so. So in order for bind to work, we need to be able to take a tree, which may contain some return nodes, and another thing, which is a function from the result type of the first tree to further trees with some other result type, and splice them together. So here's how we splice. So we walk down the first tree. When we get to a return node, we apply the second, we apply the t, the function from results to further trees, to the value being returned. And in other cases, we kind of just push it down the tree further. So we take the second thing and we splice it into the tree, the first tree, every place there's a return node. Okay, this endows M with monadic structure. To be precise, it endows ME with monadic structure for any E. But it's not actually, there's now some technical fiddling that I don't want to get too much into the details of, but this does give a monad, but it isn't quite the definition of bind that we want for convenient programming. And so we wind up doing something a little bit different, which is we define a different bind that uses that bind but that inserts one more tau. Every time we're splicing in the second tree at a return in the first tree, we add a tau. That makes definitions easier to write down, but it means that this structure with this bind is not actually a monad, really. It's a monad kind of up to tau. And we can have a long conversation about the technicalities of that. It's not actually clear which of these is better, but there are points in favor of each one. Yes.
So is the purpose of the tau constructor basically just to make more things guarded?
It's to make more things guarded, exactly. We'll see a couple of things in a minute, I believe, that would not be guarded if you didn't do that.
Is it worth emphasizing that several questions have drawn on material and co-induction that we've purposely not covered, so people shouldn't feel like they've been asleep at the wrong moment if they don't get the questions?
Yes, we should emphasize that. So for the video, Adam emphasizes that there have been a lot of questions involving technicalities of co-induction and co-fixed point and all that, that we do not expect you to follow either the questions or the answers unless you happen to know about that stuff. At a higher level, you can really just think of it as functional programming, and what we're doing is building up a data type M of descriptions of computations, and endowing it with a monadic structure so that we can use the monad notations, really. Okay. And now we can start defining some things on that basis. We haven't instantiated the set of events with anything yet. We're going to in a minute. For the moment, you can think of it as the events are, for example, descriptions of the socket system calls. But generically, no matter what the set of events is, we can define things like spin. So spin is a tree that just diverges, consisting only of taus. And tick is kind of the opposite. It's the smallest possible tree. Well, it's the second smallest possible tree that just takes one step. So it takes one tau step and then returns. And forever is a little bit more interesting. So if X is a tree, then forever X, which is defined as X followed by forever X, is something that just repeats whatever X does infinitely. And since we use the monadic syntax that throws away the result of X, it doesn't matter what its result type is. It can return something if it wants. We'll just throw it away and then execute X again. And the result type of this whole thing, interestingly, is void. Void is defined just above. It's an empty type. In other words, this definition, the type of this definition, gives you a guarantee that the result of forever is a tree not containing any return nodes.